All right, so for homework, you had these two assignments here, Chapter 5 homework number 5 and Chapter 5 homework number 6. Show how Boyle's law and Charles' law are just special cases of the ideal gas law. We've already talked about this a number of times. When you have a fixed well, it doesn't even have to be a fixed volume. When you have an enclosed volume, meaning that no moles can escape from this, then the number of particles inside of here stays constant. Because the number of particles, n, stays constant, whatever you change to the conditions, to the gas law conditions, has to then be made up for in another one of them changing. So to show Boyle's law, this is Boyle's law right here for number 26, says that V times P equals V times P. What that just tells us that we're going to keep this gas at a constant temperature. So maybe what we do is we put a piston in the top of the cylinder and we can compress the gas. And as I don't know, I had to draw it again. There it is right over there. As I push the piston downward, the volume gets smaller, so the pressure has to increase in order to make up for that, to compensate for that. Charles' law was the one that we did as a lab in regular chemistry last year that just basically says V times T equals V times T. And so in this situation, we're going to try to keep the pressure constant. So if you heat up the container, we're going to have it expand, push the piston outward so that the volume can increase to compensate for the temperature increasing so that the pressure can stay constant. So you can see from PubNert that we can use ideal gas law as a way to prove the combined gas law, Boyle's law, Charles' law. Gay-Lussac has a pressure over temperature equals pressure over temperature. So, and then even Avogadro's that we could change the number of moles inside of there and make that a variable as well. So all of that you guys can handle. Morning Angel, these kinds of questions tend to show up as parts of an FRQ where they ask you to explain something, maybe also involving kinetic theory, which is what our second FRQ today does. Question number 27 says at room temperature, water is a liquid with a molar volume of 18 milliliters. So here is our H2O in the liquid state. All right, so this is a blow up of this little tiny graduated cylinder that's in this very, very large container that's 30 liters in size. All right, so at room temperature, we know water is water. Okay, so now what we're going to do is we're going to heat it up past its boiling temperature. At 150 degrees, we know that this water is all going to boil out. And so these particles, sorry, pen won't write with me. These particles are going to then be in the vapor state. Now, in the vapor state, what happens in terms of talking about what an ideal gas is, water doesn't make a very good ideal gas because one issue with water is it likes to stick to itself. Remember us talking about polarity last year in chemistry? For those of you who are newer to this, you haven't learned about polarity yet. So a question like this one really needs to be saved. If we're going to go very deep with this question, it needs to be saved for later on. There's an attraction between the oxygen of the one water molecule to a hydrogen ear of another water molecule. We call that hydrogen bonding. And so therefore, that's why water is still water all the way up until we get to its boiling temperature of 100 degrees Celsius. Once we get to 100 degrees Celsius, these particles with kinetic theory are moving so fast that they break free of each other. And so now inside this larger container, they're moving around with a velocity that doesn't allow them to stick to each other, and then also actually creates, you know, if we were to put a little tiny pressure gauge on the side of this container like so, this pressure gauge is going to read 1 atmosphere of pressure because of those water molecules colliding with the mechanism of the gauge. Okay, so I don't know, explain the large difference in molar volume. Gas particles don't stick to each other like they do in the liquid state, and they have a high velocity which allows them to take up that entire space of the 30 liters. Okay, haven't quite mastered how I make the chat stay on the screen here. Won't even show me it at all now. Why is it again that the boiling is a cooling process? You won't be asked that question currently. That question is going to come up though next chapter, because in chapter 6 we start talking about thermodynamics. The reason why boiling is a cooling process. Now we have to consider what's being cooled. Okay, so now if you want to consider the water that's left behind as the hotter molecules leave the water and become a gas, you're taking away the ones that have a higher kinetic energy. As you take away the ones that have the higher kinetic energy, the ones that are left behind have lower kinetic energy. So that's how our sweat works, right? When we bring the water to the surface of our body, in order for them to leave our body, they have to take kinetic energy away with them in order to have enough to break free of your skin molecules, right? And so as they do that, they cool down what's left behind because you have less kinetic energy there. So anyway, but that's not on this test, so I'm just going to keep moving. But chapter 6, we will combine this together, so you can expect your chapter 6 test or your final exam to incorporate both of those things together. So we'll be ready for that then. Question number 28, consider a sample of gas molecules for the following questions. How is the average kinetic energy of the gas molecules related to temperature? What I told you in your notes is that temperature is directly related to kinetic energy. In fact, for AP chemistry, we even have a formula. I think I'm actually going to use that formula in a few minutes. So therefore, I don't need to talk too much about this, except that you can see that because of that equal sign, that kinetic energy and temperature are directly related to each other, as long as it's in Kelvin. How is the average velocity of the gas molecules related to the temperature? Well, if kinetic energy is related to temperature, and kinetic energy has this formula, as the temperature goes up, kinetic energy is going up. As the kinetic energy goes up, something on this side of the equation also has to go up. Now, the mass, that's going to stay constant because that's just whatever the gas particle's mass is. So therefore, what happens is the velocity has to increase. Remember, this V here is not V for volume, it's V for velocity. That's why a chemistry textbook likes to use U instead of V, because they don't want you to get confused. I think that's a poor choice. I think that V is a better choice because every other science class uses a V for velocity, and you can handle that V is velocity and that V is volume. Okay, so there's even other ones too. In fluid dynamics, there's also a V that looks like that for rate of flow of a fluid. In electromagnetism, there's the nu for frequency. So there's a lot of different letters that kind of look alike. You know what they are based on what the topic is. How is average velocity of the gas molecules related to the molar mass of the gas at constant temperature? So what I did is I picked two gases. I picked something that's large, like let's just pick on water molecules, H2O, those are large. Let's pick something small like helium, okay? Now, if we put them at the same temperature, then we know that the kinetic energy of both of them have to be the same, right? Just because the helium's smaller doesn't mean it has less kinetic energy. Temperature is directly related to kinetic energy, all right? So if you have two particles that have completely different size, how do they have the same kinetic energy? Well, the larger ones have to have a slower velocity, lower velocity, and the smaller ones have to have a higher velocity. So they make up for their size by their speed, okay? Good concept questions there in number 28. Calculate the kinetic energy of the methane molecules in the sample of methane at 217 and at 546 Kelvin. So here is that formula that I was just talking about that you are welcome to use. I don't believe there's a time on your test that you're going to use this formula as it is, but there could be a time on your test where you could comment on that formula, right? Where you would actually do something that relates to it, but doesn't require you to actually plug anything into it. So my people are in the way here. I'm going to just move this over just a little bit so I can see all the numbers here. I'm just showing you how this works. And the only reason I think that I need to show you how this works is I feel like I should just point out that notice that in the numerator that we have the 8.31 number, which is supposed to go with 8.31 lakpa/moles. Okay, that's the units of 8.31. But it turns out something that we don't need to know, but in case you see it, I don't want you to be, bothered by it, is that a liter times a kilopascal actually multiplies together in a physics formula to equal a joule. And the only reason that's important is because that makes our kinetic energy come out to be joules per mole once you do the math of this problem. So it's saying that the amount of energy per mole of methane molecules is such and such. Now, when you do both of these problems, what you're going to find out is whatever answer you get here, this answer here is twice as much. So that means when you double the kinetic energy, when you double the temperature in Kelvin, you double the kinetic energy. You can plug those in and solve that yourself if you really like to know those numbers. Question number 30, calculate the root mean square velocity of the methane molecules in a sample of methane at 273 and at 546. You do not have this formula on your chapter test. There could be a time that you could make mention of it. I don't even think that there's really even a space on this chapter test that you'd make mention of this. But you might on your final, because I have to find the FRQ that I've given you for this chapter test is a lot like the lab. That's why it's recommended that you finish the lab up before, see, the lab is due. Oh, your test is on Thursday. I keep thinking your test is tomorrow because tomorrow in school terms is tomorrow and AP Physics has their test tomorrow. You guys have your test on Thursday, which means you'll have already turned in your lab ahead of time or else it's late. I would suggest doing the lab because the lab is really practicing the big FRQ for the chapter test. So you might as well do it so you kind of take care of two things at once. For your final exam, I've been trying to write my own FRQ, and I can't believe how hard it is because I just keep thinking about how smart some of you are and that you could say, but Mr. Purser, if you drop this into that, you just change the overall volume, which means now we have to completely adjust the problem. I'm thinking, you're right. So I'm like, I can't write an FRQ on my own. Sometimes I have to actually rely on other ones. So I will be looking for other FRQs in the released AP tests. You should too. But most of them mention something about kinetic theory. And so that's when equations like this could be brought up, where you could say that if this is velocity, root mean square velocity basically is just a fancy way of saying the average velocity. It's a statistical thing. It's a root mean square has something to do with the bell curve that says that you have these methane molecules. Some of them that will put velocity on this axis, and we'll put the number of particles on this axis, velocity. What this says is that the majority of them have this speed. Some of them are traveling faster, some of them are traveling slower. And what root mean square does is finds the average of a bell-shaped curve. That's all that is, okay? So I want you to know that if you ever encounter this equation, they're just basically talking about a statistical average. We don't need to know anything more. What would you say about this conceptually? The higher the temperature, the more statistically we'll have enough velocity to do whatever, like turn into a gas, right? What if you could make this bell-shaped curve by heating it up, by increasing the temperature, you could cause this bell-shaped curve to go over to here instead. Now you can see that if there was something special about this spot right there, that midpoint, right, the highest point of the first curve, now you have in the blue, you have more particles that are actually past that special point. So whatever it is that happens, like evaporation, turning into a gas, more particles have the ability to do that. That's the most that you would ever use that equation, is just to conceptually explain it. So I'm going to stop talking about it and just give you the two answers that are there. I would not spend any time focusing on that problem. Question number 31, do all molecules of a 1 mole sample of methane have the same kinetic energy? Hey, I just explained that to you with the bell-shaped curve, right? If this is there, now instead of putting velocity on the x-axis, let's put kinetic energy on the x-axis. The average says that based on whatever temperature we're at, it averages to some kinetic energy. But that doesn't mean they all do. Some of those CH4s have more kinetic energy, and some of those CH4s have less kinetic energy. such that when you average them all together at whatever temperature this is, it averages to that number. That kind of brings us to Kumar's question earlier, is boiling being a cooling process. If we say that maybe right here is the temperature that corresponds to boiling, what happens is all of these particles over here are all going to turn into a gas. When they do that, what's left behind inside the liquid is the slower ones. The slower ones have less kinetic energy, therefore they have less temperature. So kinetic theory says that boiling is a cooling process because the higher temperature, higher kinetic energy particles leave. And the ones that are left behind are the slower, lower kinetic energy, therefore lower temperature particles that are left behind. But the answer to this question, do they all have the same energy? No, it's an average. So therefore some have more, some have less, so that the average is the average. Question number 32, we now are on to the second assignment. Consider a 1 liter container of neon gas at STP. Will the kinetic energy, average velocity, and frequency of collisions of gas molecules with the walls of the container increase, decrease, or remain the same under each of the following conditions? The temperature is increased to 100 degrees Celsius. Okay, so that means then in part A, we can say what increases is the kinetic energy, right? Higher temperature, more kinetic energy. Also what increases is average velocity. Also what increases is frequency of collisions. So I'm going to say all of them increase. Okay, letter B. The temperature is decreased to -50. I'm going to do just the opposite. Everything here is going to decrease. The kinetic energy decreases because they're at a lower temperature. Velocity then decreases. Frequency of collisions decreases because if they're moving slower, they're not going to collide as often. The volume is decreased to 0.5 liters. So now we take this container, which was a 1 liter container, and let's squeeze it down to a container that's now only this big. So now I put 8 particles in there. Let's put 8 particles again in there. 1, 2, 3, 4, 5, 6, 7, 8. I think that's 8. What can we say about them? Well, at 0.5 liters, their temperature didn't change. So we would say that the kinetic energy, stays same. I'm going to say the kinetic energy stays the same. I'm going to say the velocity stays the same because temperature didn't change. But I'm going to still say that because there is less space for them, the frequency of collisions is going to go up. Okay, does that make sense? Because that's a good concept question there. How about if the number of moles of neon is doubled inside the container? If the number of moles inside here is doubled, so let's go back to the original container and let's add 8 more particles. 1, 2, 3, 4, 5, 6, 7, 8. If they're still at the same temperature, kinetic energy is going to stay the same. If they're still at the same temperature, velocity is still going to stay the same. But because there's more of them, the frequency of the collisions is going to increase. Okay? Take a question like number 32 very seriously. I can pretty much 100% guarantee, 100% pretty sure that your final exam will have an FRQ on gas laws where this gets incorporated into that problem. Okay? I know that the AP FRQs are littered with kinetic energy, kinetic theory problems attached to gas law problems. It just so happens, though, that the one I picked for your chapter test doesn't, because it's based on the lab that you're doing, and therefore it is what it is. But just know that I've got to find something different for your final, and therefore I'm going to find one that has kinetic theory attached to it as part of it. So be ready for number 32 for your final. Question number 33, consider 3 identical flasks filled with different gases. There is a question like this on your chapter test. In which flask will the molecules have the greatest average kinetic energy? What do we know about kinetic energy? It's directly related to temperature. So you look at their temperatures, and what you notice is they're all the same temperature. Therefore, all 3 flasks, we would say, all have the same kinetic energy. Good. Question letter B, in which flask will the molecules have the greatest average velocity? Okay, so we now know that they all have the same kinetic energy. But we know that the kinetic energy has a formula that says 1/2 mv squared. So the one that will have the greatest velocity is the one that has the least amount of mass. So the smallest mass is our hydrogen gas, and so therefore hydrogen will have the greatest velocity. It makes up for its small mass by having a higher speed so that it can occupy the same volume as a bigger gas that's at a lower speed. Notice that I didn't do anything with the pressure. Notice that I never even considered these things right there. I don't think we need to because we don't really have a direct relationship to pressure here. The only thing that I could have done with the pressures is I could have used the pressures and temperatures to maybe find, you know, I could make up 3 identical flasks. I can say they're all 1 liter, so the volume is the same. And then I could solve to find out how many moles of each particle we have. But is there any reason I need to know the number of moles? They didn't ask us about anything about how many particles were there. They just asked us, of those particles, who has more kinetic energy and who has a greater velocity? Those things aren't tied to moles. Okay? Question number 34. You should also, I think you have this on your test. I know that this is on the in-class version of the test, so it's possible it didn't make it on your test that's right now, but you have access to it, so you can handle it. When they put this one on the AP test, the goal here is that you wouldn't need to actually do a calculation. The goal here is that you could solve this one by just looking at the situation, okay? So let's talk about this situation, because in class we didn't really get a chance to work on this together because the class was dragging on too long. I said to you, just do it for homework. So here it is. Okay, so first of all, you need to recognize an effusion rate, all right? Because the formula says you need the rate of effusion for 2 different gases. So how do you know what an effusion rate is? Well, some people might know it by its units, the volume per minute. Not me. How I know this is an effusion rate problem is because it begins by saying the effusion rate of an unknown gas is this number. So I now know that the effusion rate for gas unknown is 31.5. And then they tell me the effusion rate of oxygen is found to be 30.5. So I have those 2 rates, okay? Now, if I call the top one the unknown, and I call the bottom one the oxygen, notice that on the other side of the equation, it flip-flops. It's an inverse relationship to the square root of its mass, or its molar mass, really, okay? So the unknown is on top on the rate part, but it's on the bottom for the molar mass part. Why is that? Because remember that if we're saying that the Ke for the unknown equals the Ke for the O2, and you've got 1/2 m times v squared equals 1/2 m times v squared, we can cancel out the 1/2s, and now you have the mass of the unknown times its velocity equals the mass of the oxygen times its velocity. If you now divide the mass here, let's divide this mass to the other side. You have mass, sorry about my bad writing, but I'm just trying to hurry here. You have mass of O2 over mass of the unknown. Then if you divide the velocity to the other side, you get velocity of the unknown, which is already there, divided by the velocity of the O2, okay? Now, because of the squares, if you square root both sides, now it becomes that equation right there. Nobody's going to ask you to derive it, so therefore I didn't spend any time doing that in class. But it couldn't hurt to see where this comes from. Had we been in class, I would have done that extra credit with my glass tube and the effusions, and then I would have actually addressed this as an extra credit. But we, with block schedules and not being together, that got kicked to the curb. Here you have this formula. Now, look at the formula. I put in everything here. The molar mass of the O2 goes on top. The rate of effusion of oxygen goes on the bottom. The rate of effusion of the unknown goes on top. The rate of the molar mass of the unknown goes at the bottom. Look at the relationship here. These 2 numbers are almost the same, with this one being just a little bit smaller. So what I need for this equal sign to be true is I need this number here to be almost the same, but just a little bit smaller. That means nitrogen dioxide, you're out. Carbon dioxide, you're out. Methane, you're out because even though you're smaller, you're way too small in comparison. So if this was an AP multiple choice question without doing any math, I would say the answer is the nitrogen monoxide because its mass is just a little bit smaller than the oxygen mass, such that the rates come out to be slightly different as well. Now, if I have the time, I'll actually solve it. I'll actually solve this equation and guarantee that I get 30 instead of 28, right? Because there is a square root there. So maybe I'm wrong. Maybe it's the 28. But if I was taking an AP test, the minute that I can narrow things down to a 50-50 guess, that means you're going to get a 50% on the AP test. That's an F. Just kidding. The pass rate on the AP test is down usually in the like low 40s or high 30s, which means that you can get a really bad F and still get a college credit for this class. So if you ever get to narrow something down to a 50-50 chance and you don't have time to actually solve it out, you should walk away confident because you just won the gambling aspect of the AP test. Now, the current AP test hasn't been that way. Time hasn't been an issue until this last year with COVID, but then they didn't have any multiple choice questions, so therefore it didn't matter. Question number 35, come on, easy. Calculate the pressure exerted. They give you a moles, they give you a volume, they give you a temperature. They want us to practice using the ideal gas law. Why this was thrown in the middle of this, I don't know, but I picked it. It was in your textbook. You solve it out. You get 12 atmospheres. If you use Latam Camol, right? There was nothing here telling me I had to use Latam Camol. You could have chosen to use Lakapa Camol or Latour Camol, and it's just your answer would come out to be a different unit. How do you know which one to do? Well, if it's a multiple choice question, look to see what the units of the answers are. If it's a part of an FRQ, look to see what the units of the other parts that you're doing are. But in terms of if it's a like part one of an FRQ and they don't tell you what units to put it into, you have the freedom to put it into whatever you want. It's just that you might have to change it for the next part. So that's why when we get into the FRQs, I'm going to purposely try to pick the units that speed up, make the problem more efficient, right? But otherwise it doesn't matter. All right, that brings us to our review. Now, it's only 8:30. Like I said, I need to be done by 9:20 because I need to have some time for regular physics to get their stuff ready. So we have plenty of time. We have 50 minutes if we need it, which means that you could go for a potty break right now. You could go get yourself a donut or something, whatever's in the kitchen. And you can, if you haven't looked at these review questions yet, why don't you look at this right now and see if you have an idea? Jot down what you think the answer is to A and B, and then we'll go over it. And I'll give you like 3 minutes. No, let's give you 4 minutes because you might need to go for a potty break. Good morning, Marissa. Good morning, Raina. I'm not sure why it's letting Yvette and Maria be above you on the Zoom list. Usually it puts the people who turn their videos on to the top of the list. So Raina, you're being mistreated here by Zoom. You should file a complaint to the Zoom authorities. There might be a way for me to switch the order of them, but I don't know how to do that stuff. Pearl, the answer to that is yes. All right. I opened up the chat over here on this computer. Of course, nothing shows up. But just in case it closes on me and you need to ask me something. Remember that if you're asking me something in the chat and I haven't responded to you, please feel free to unmute and just say, could you check the chat? And I will check it. I know I said 4 minutes, but you probably didn't need more time than that if you were just making a quick guess here. As you push down on the syringe, how does the membrane covering the test tube change? Okay, so let's consider what we know inside of this closed container here. That the way this is set up with a non-permeable elastic membrane, I think we call that a balloon, right? Like a latex balloon or whatever you're thinking right now. It could be a condom. It's just something that it allows that there's some flexibility to it. It's covering the top of this, all right? Now I'm gonna assume that when they set this up, that everything was equalized in pressure. So the pressure inside the container, I'm gonna call that P sub C for the container, is the same as the pressure inside the test tube. I'll call that P sub T for the test tube. So because they're the same, the membrane, the rubber balloon, is perfectly straight across right there, according to what I see in the picture. Now we push down on the syringe. By pushing down on the syringe, I think we all recognize that the air that's inside of the syringe, or I mean, it could even be a liquid if you're thinking like it's like a needle for a shot or something like that. Whatever it is going to inject particles into this container. I'm going to stay with the air theme. If you inject particles into this container, you're putting more particles in there, which means you're going to cause the overall pressure inside the container to increase. If the pressure inside the container increases, then what's going to happen is it's going to push the membrane down like this in order to compensate so that it has more volume inside the container, so that the pressure inside the container goes back to equaling the pressure inside the test tube, right? So we're going to see that membrane push down just a little bit to equalize pressures inside and out of the whole apparatus. You stop pushing the syringe, but continue to hold it down. In a few seconds, what happens to the membrane? Well, I don't like the idea that anything changes to the membrane. I want the membrane to stay in that position because it doesn't say that it's semi-permeable. It's not saying that the air inside of the inside the container is able to seep through the membrane and allow them to equalize pressure inside and out so it could go back to being flat again. I'm going to stay with the answer is it stays the same. And this question is all about pressure. Pressure changes because if you increase the number of moles, PV equals nRT. By increasing the number of moles inside the container, when you push down the syringe, you increase the pressure inside the container. If the pressure inside the container is greater than pressure inside the test tube, that membrane is going to have to kind of almost look like a meniscus in order to make up for that. Question number 2. I'll give you a moment to look at that one and see if you know, how does the barometer work? Now, let's treat this like an AP multiple choice question. Not only do you want to try to find the right answer, why don't you try to see if you can eliminate wrong answers? Because passing the AP test might not be just about getting the right answer. It might be about improving your odds by getting rid of wrong answers. All right, I'm going to go to the next slide where I have underlined some key bad words. Key bad words. Anywhere that it says air pressure inside has to be wrong. And the reason for that is because it shows you right in the picture. There is no air pressure inside. This is a vacuum sitting above the mercury, and therefore, no matter how hard you push down on the mercury, you can't cause the pressure inside to equal the pressure outside. That was a true statement in this problem because there were particles of air inside this test tube. And so therefore the gas inside the test tube can exert a pressure, and if you push on it, it'll push back. But if you push on the mercury, there's no air in here to push back. So right away, A and B are out. The minute that A and B are out and you only have choices C and D, you get a little bit of a smile on your face as you say, I now have, by the odds, passed this AP chemistry test. Now, why is C the better choice? Well, because that's the way I described it to you when we were learning this the very first day of chapter 5, is that the air pressure outside pushes on the mercury until the weight of mercury inside the barometer, inside the glass tube, is equal to the pressure on the outside. Why is it not D? Because we never ever mention the words capillary action. In fact, when you guys come back, we will do a lab that involves capillary action. And what you're going to see about a capillary tube is about this thin, right? In fact, there's a good chance that you're going to break my capillary tubes when you do the lab. That's why the people who gave us the lab gave us like 50,000 of them, because they know that the students are going to break them because they're so small and delicate. Now, what's special about them? They're almost as thin as a needle, and they're made of glass. And because of the thinness of them, the weight of the liquid that you put in them will actually get kind of, I don't want to use the phrase sucked up in there, but it sticks to the walls of it and doesn't fall out of it like a straw because it's so thin. So capillary action really is more of an attraction between the liquid or gas, in this case liquid, and the sides. Now, another thing about capillary action is mercury has no attraction. Mercury is as a liquid atom, liquid substance, the HGs, they have no attraction to the other HGs, which makes them perfect for doing things with using gas pressure against liquids because of the fact that they don't stick to each other. Water molecules will break that rule a little bit, but mercury won't, so therefore that's not a good choice either. All right, good job. Next one. I told you I used to have a tube like this, and I broke it because in 22 years, there's a really thin, delicate piece of glass. There's a good chance I'm going to break it. I don't think I spelled below correctly. Isn't it just one L? The barometer bellow shows the level of mercury at a given atmospheric pressure. Fill all the other barometers with mercury for the same atmospheric pressure. So at least mentally fill them. Hopefully what you're thinking right now is if the atmosphere is pushing down on the surface of this mercury such that in the very first tube, it pushes up the mercury to, well, let's not say it pushes up. Remember that we would start with this tube completely full. Then we would invert it into the liquid trough that is down here at the bottom. And then the mercury is going to fall to a point where there's a vacuum up here. And the weight of the liquid is exactly the same as the pressure pushing from the atmosphere. So if you made barometers out of the rest of these tubes, let's say that you filled up this one also all the way to the top with mercury and then inverted it down into the mercury bath, what's going to happen is the mercury is going to drop until the level is exactly the same as the level in the first one. It doesn't matter how wide the tube is because pressure doesn't care about that. Pressure already incorporates area, cross-sectional area into its formula. In this one here, a skinnier tube, same thing. Now, you could make an argument that in this tube here, if some capillary action was possible, maybe this tube would actually go a little bit higher. But it is mercury, and mercury doesn't exhibit that kind of attraction to the walls of the container. Therefore, it should be the same level. This one here, it doesn't matter that it has this fatter part. It's still going to fill it up. It's still going to, when you invert it down into the mercury bath, it's going to drop to that same level. It doesn't care about the shape. This one here, because it's already shorter than the maximum height of the mercury, this one's just going to stay full all the way to the top. Just like you would do with a flask, right? In fact, that is shaped like a flask, that you invert that down into the water. I should have probably showed that step in the virtual lab, that I just wanted to speed things up with the lab so that you didn't, get bored. but mercury's going to go all the way to the top. Questions 4 and 5. Give you a minute or two on these also. You guys have two formulas that have density. Gas density had the formula molar mass equals dRT over P, and density equals mass over volume. So as we, this is just the first week of school kind of formula. First week of, or third week of regular chemistry kind of formula. As you increase the temperature of a gas in a sealed container, what happens to the density of the gas? Would the results be the same if you did the same experiment in a container with a piston at constant pressure? Okay, so let's start with using the container from number 5 as our rigid sealed container, because wouldn't this be rigid and sealed? It's sealed with a rubber stopper or a cork stopper, and it's rigid, meaning that it can't change its shape. Okay, that's what rigid means. So you're going to increase the temperature on this. So you put fire underneath it. Okay, as you increase the temperature of it, we all expect by kinetic theory that the particles are going to move faster. So the particles are going to increase their velocity so that they're colliding with the walls of the container a lot harder. In fact, if we had a little tiny pressure gauge on the side of this, we would see the pressure gauge go from reading something small to reading something really large. Okay? In other words, if you increase the temperature, you're going to increase the pressure to compensate for that. Okay? Now, could it be instead that it increases the gas density? I mean, or maybe decreases it or does something to it? Well, consider what density is. If density is the mass divided by the volume, has the mass of the particles changed? No. If it's a rigid container that can't change its volume, has the volume of the container changed? No. Therefore, the gas density does not change. Just because you heat it up doesn't make it have a higher density. It keeps it the same. What changes to compensate for it is pressure. Back to just the old combined gas law, pressure changes with temperature changes. Now, would the results be the same if you did the same experiment in a container with a piston at constant pressure? Okay, so then what you're thinking to yourself is, let's draw the picture for a container that has a piston in it. Put our particles in there, and let's heat it up. As you heat it up, we expect the piston to start to move backward. As it moves backward, it does that to compensate and keep the pressure inside and outside constant. But what it does is it changes the volume. The volume goes from being small, the volume goes to being big as the cylinder pushes out. So now, if you think about the formula for density, did the mass of the particles change? No. But did the volume of the container change? Absolutely it did. Therefore, we would say that the density decreases in the second, I can't spell decreases in the second half of this, and it stayed the same in the first half of this. Maybe we're starting to see why people don't pass the AP test. How do you feel like these questions would go if you were all by yourself, alone, even if you're in a room full of 18 other people, but you're taking a test in AP chemistry, and these are the kinds of multiple choice questions that you see? Could you logic these out, right? You'll notice, and this is what I said to you at the beginning, I didn't get your homeworks graded because I was busy making these slides. Now, making the slides wasn't writing all the stuff that was on the PowerPoints, that was already there. The making of these slides was me writing down all of these words to make this go faster, right? Because I too have to think these out. It's not like I look at question number 4 and I know the answer. I have to think about, what is gas density? What is a sealed rigid container? And then everything starts coming together and it's like, oh yeah, easy. This actually is really easy if you draw it out, if you think it out. What are the formulas? What are you able to change in the formulas, and so on and so forth? Question number 5, a diagram in a chemistry book shows a magnified view of a flask of air as shown. What do you suppose is between the dots? The dots represent the air molecules. more air molecules, right? That's what an 8th grade science student would say. An 8th grade science student would not be able to accept that there's nothing in between these particles. It's a vacuum. What's in between here is a vacuum. So why don't all gases just get sucked up into a single point, a singularity? Because they're moving. Because they're moving, they push on the walls of the container. If you continue to cool this flask down, you're going to cause these particles to kind of try to come closer to each other. And what they're going to try to do is actually implode this glass by the lack of pressure inside of there if you cool them down. So don't put fire, put ice. Right? So what's in between the particles? You all recognize that there's nothing there. It's a vacuum. Crazy idea. An 8th grader can't handle that, but an 11th grader better be able to handle that. Keep on moving. If you put a drinking straw in water and place your finger over the opening and lift the straw out of the water, some water stays in the straw. Explain why. Okay? Well, first of all, the straw is thin, which helps because then we don't have an issue in the center where the liquid can actually fall out of its place by the fact that the water will make a U at the bottom of this and then it will drain. So this really only works for thin tubes. Unless you have it down inside the soda, then it wouldn't matter how thin the tube is. But while it's in the air, what we recognize is the soda is going to fall to a height so that the pressure above the liquid, this pressure inside here, is equal to the pressure outside here of the atmosphere. And this outside pressure is pushing up on the bottom of this, and then, it's pushing everywhere, but including it's pushing on the bottom of this so that the liquid doesn't fall out of there until you take your finger away. Now, if it were to try to fall out of there, it's going to make this area of straw bigger. That's a bigger volume. If the volume increases, the pressure decreases. You create a partial vacuum above your liquid water in the straw or liquid soda, whatever's in the straw. It can't do that, so it stays in there so that the pressures inside and out stay constant. Good times. Question number 7. If you have any two gases in different containers that are the same size, at the same pressure, and at the same temperature, what's true about the moles of each gas? So of course, people, if you were taking a test, would just jump on the answer. They're the same because everybody else is the same. So maybe it'd be smarter for us to actually draw it out. I made 2 volumes, said V1 equals V2. I made P1 equal to P2, and I made T1 equal to T2 because they tell me that those are the same. Then I looked at the ideal gas law and I solved for N. And then I go, oh, they are the same. Sometimes your knee-jerk reaction is the right reaction. So N would be the same. Why did they ask us that question? Because they wanted you to be thinking about how could oxygen, which is really, really big diatomic molecules, take up the same amount of space as hydrogens, which are really, really small diatomic molecules. How could that be? Because in the kinetic energy formula, if they're at the same temperature, the Ke here equals the Ke here. The 1/2 big M times little v squared equals the 1/2 times little m times big V squared. So what do the little hydrogens do? They make up for it by having more velocity so that they can still exert the same pressure on the walls of the container as the bigger particles. Those of you showing your faces look really excited right now. But it wouldn't be any different if you're in here, right? You wouldn't look very excited. Question number 8, I'm not going to waste your time on this one unless you ask me to. Question number 8 is just good practice at doing PubNerd. They have something not given, and you're supposed to solve. And notice that each time they gave a different measurement for pressure, so you might want to use a different ideal gas law constant based on what's there just to make the problem faster. I'd be happy to go over any one of those if anybody did it ahead of time and needs the help. Otherwise, if you need help on this, you can still email me before Thursday. Keep on going. Question number 9. A compound has the empirical formula CHCl, a 250 ml flask, 373 Kelvin, 750 torr, contains 0.8 grams of the gaseous compound. give the molecular formula. Okay, so my first thought when I saw this problem was molar mass equals dRT over P. But then I thought about it and I'm like, well, I don't know if I like that formula because what on earth am I going to do with the gas density part? I could make that formula work. But before I do that, why don't I write down the givens and just see what I think? As I wrote down the givens, I'm like, oh no, this is just back to just simple stoichiometry and ideal gas law. If we take the 0.8 grams of mass, I can't do anything with that. Never mind. I was going to say, let's do this. You can't, because when you go to get out of grams and get into moles, what are you going to put in for the grams if you don't know the chemical formula of the molecule? We only know the chemical formula of the empirical formula. So what I know is going to happen when I see an empirical formula is I know that we're going to take the empirical formula and we're going to multiply it times something. So therefore what I did is I found the molar mass of the empirical formula. Just added 1C plus 1H plus 1 chlorine and got 48.5. Now, what I'm going to do is use these to find out the number of moles. Here's where the ideal gas law comes into play. So N equals PV over RT, which means that you're going to plug in 750 torr times, because I'm using torr, I'm still doing volume, so 0.256 liters. Then, because I'm using Latour, I'm going to use the 62 point, see, I already left this out because I knew that I would have to look it up because I never remember if it's 62.4 or 62.8. Okay, and then times the temperature of 373 Kelvin. Multiply those out, you get the number of moles. I don't think I have an answer slide because I didn't put an arrow on this one. So let me just do it real quick. 750 times 0.256 divided by 62.4 and also divided by 373 equals 0.0082. That's the number of moles. Now, if we take the mass divided by the moles, we now know the molar mass. 0.8 grams divided by 0.008 moles. Now, of course, even though I wrote it down like that, I'm using the number that's on this screen. 0.8 divided by answer comes out to be 96.98. All right, we're in business. 96.98 grams per mole. If this has a mass of 96.98 and the empirical formula has a mass of 48.5, sounds like the multiplier is a 2. So it sounds to me like we can say C2, H2, Cl2. Aha. Empirical and molecular formulas, gas laws, good stuff. Man, we are running out of time. Calculate the density of ammonia. You're going to use this formula. The molar mass of ammonia is 17. Oh, they should tell us that. On an AP test or a chapter test, they would tell us the chemical formula of ammonia. Once we know it's NH3, 17.0 equals D times, since they gave us torr, sorry, I had a brain fade there. What was I going to use for the ideal gas law constant? 300 Kelvin and pressure of 635. Because they gave me torr, I'm going to use the 62.4 number, and then I'll solve that and it will give me the density. I don't have an answer slide, so I have to move on. Question number 11, they gave us masses of our two gases. We place them in a 1 liter container at 27 degrees, and we want to find the partial pressure of each gas in the and also the total pressure. I wrote a note that said partial pressure matches the mole fraction. So therefore I don't know. I probably still would just find the pressure of each gas on its own anyway. So I don't even think I'm going to mind my first line there. I think I'm going to start by saying 1 gram of H2, and I'm going to get out of grams, and I'm going to get into moles. 2.0 grams per mole. tells me I have 0.5 moles. Okay. Then 1 gram of helium at 4 tells me I have 0.25 moles. Never mind, I am going to use my first note. Why would I convert these to pressure? Well, I guess I have to. Yeah, never mind. I'm still not going to use my first note because the answer does say, give us a pressure answer. It doesn't say, tell us the fraction. It doesn't tell us the percentage. It says, find the fraction. So therefore, I will use Puvner. nRT over V. We have a temperature. We have a size of a container. Plug those in to find the pressure of each one. Put those in here and then solve for the total. Definitely something, a skill set you're going to have on this chapter test, I hope. If you don't, well, good luck on that test. I'll move on. Question number 12, is this the last one, I hope? Helium is collected over water at 25 degrees Celsius and 1 atmosphere total pressure. What total volume of gas must be collected to obtain 0.586 grams of helium? Man, this just sounds like the free response question on the test, doesn't it? First thing that I might want to do here, what total volume of gas must be collected? So this is what I want, is to know what volume of helium. Money question. How do I get that volume? I feel most comfortable finding the volume of helium by taking nRT over P. But if I'm going to do that, I've got to have the number of moles of helium. Okay, that's easy. We'll just get out of grams and get into moles. Okay, once you get that answer, that's going to go in here. We need a temperature. That's easy. They tell us it's at 25 degrees Celsius. That's going to go in here. What we need, though, is a pressure for the helium. We can't use 1 atmosphere because the amount of gas that's collected in there when it does equal 1 atmosphere doesn't just contain helium. It also contains water vapor. You have this on your test. You have this on your lab. Make sure you understand it. So what I'm going to do is I'm going to take the P total equals the P for the helium plus the P for the water. P total is, because they gave me the partial pressure in torr, I'm going to use 760 torr instead of 1 atmosphere, and then solve for the helium. Oops, 23.8. Subtract 226.2. No, not 2. 726.2, something like that. I'm trying to hurry now because at this point we're starting to run out of time. Now that I know that pressure, let's plug that in here. Bang, we got it. There's your volume. Your lab works and solves for a different variable, right? It solves for N, I think, if I remember correctly. And then you do a comparison of that to the theoretical yield. But I could be wrong. It could be solving for V. It could be solving for P. It doesn't matter. You can solve for any one variable. That's a good question right there, number 12. I would definitely put a star by that one. Take a screenshot. Do whatever you got to do. So I'm going to turn the page. Go once, twice, turn the page. FRQs, finally. 19 minutes, 2 FRQs. Think we can do it? Me neither. But you know what? These are they're online, right? Especially the second one because we know the year. So therefore, you can look these up yourself. You guys know that you're in an AP class, right? You know that there's a lot of the stuff that you should be doing on your own without my help. I know. I just went mountain biking yesterday with an ex-student who's a senior at UC San Diego right now. Sat in the same classroom just like you guys, taking these classes. And he says that all of his best classes are the ones that are all asynchronous, meaning that what you're doing right now would all be done by a video lesson that you watch on your own time. And I say, Nigel, I agree with you wholeheartedly, but I'm not allowed to do that. I have to Zoom these because there's something about the fact that I'm getting paid. They just don't trust teachers to do it right. So here we are. So you can go back and watch these, but I'm not going to have time to finish the second question. So therefore, you have to actually look it up yourself. A sample of pure gaseous hydrocarbon is introduced into a previously evacuated 1 liter container. The pressure of the gas is 0.2, temperature of 127. Calculate the number of moles. Now, obviously, I'm not going to give you enough time to solve this right now, but you should be thinking, can you solve this? right? So the kinds of things that you're going to do for me on your test, because you know it's going to get you partial credit, you're going to draw a picture. Maybe you're going to label this as V equals 1 liter, and then you're going to put hydrocarbon in here. I like to abbreviate hydrocarbon as affectionately HC. It's got carbon and hydrogen in it, so let's call it HC, but we just don't know what it is. Okay, so now what else do I know about this? I know that when it's all said and done, its pressure is 0.2 atmospheres, and I know that the temperature is 127, which I believe is 400 Kelvin. Hey, look at that, V, P, and T, and they ask me how many moles of this hydrocarbon is inside of there. AP FRQ, this is an actual test question? Yes, it was. So I don't know if I can tell you what year. I can't. I never wrote down what year this one came from. So it could be anywhere from 2011, 12, 13, somewhere in there is probably where it came from. Doesn't matter. We're going to solve it right now. We just won't get to the second one. So to solve for PubNert, N equals PV over RT equals 0.2 atmospheres times 1 liter. Because they gave me liters and atmospheres, I feel more comfortable using 0.082 latam per mole, and then temperature of 400 Kelvin. Come on, anybody going to miss that on a test? You have a question very similar to this one on your chapter test. 0.006 of hydrocarbon. Now, part B. Hey, you can still use your same picture on the test tomorrow. Somebody introduces oxygen in here. Containing hydrocarbon. After the addition of the oxygen, the total pressure goes up to 1.4. Calculate the partial pressure of the oxygen in the vessel. Come on, piece of cake. You were all thinking that, right? Pretty easy stuff. These FRQs should not be outside of our wheelhouse. Don't forget units. I will grade units. Don't forget significant digits. So 3 significant digits, 3 significant digits, I put 3 in my answer. So I will be grading those kinds of things on your test. Those are just ticky-tack points we don't want to lose. Okay? That's the easy parts. After we get past the easy parts, we get to the parts that now separate the 4s and 5s from the 2s and 3s. There's nothing wrong with being a 2 or a 3, especially a 3 because you still get college credit for it. A 4 or 5 is nice, but it's not every single question is going to be 4 or 5 worthy. The mixture of the hydrocarbon and oxygen is sparked that a complete reaction occurs producing CO2 and H2O, okay? So my first inclination for this is HC plus O2 is a combustion reaction that produces CO2 and H2O, okay? Now, the partial pressures of these gases at 127 is 0.6 atmospheres. I don't need the significant digits when I write this down like this, and 0.8. There is O2 remaining in the container after the reaction is complete. Okay, so I'm assuming that the fact that they tell me that the reaction is complete tells me that we completely burn the hydrocarbon. So what I'm actually going to do is I'm going to rewrite this. I'm going to do this the way second semester is going to look. We're going to say initial and we're going to say final. All right, and so what we would say initially was we were at what, 0.2 atmospheres of this and 1.2 atmospheres of this. And then in the final conditions, we're down to 0 atmospheres of this. We were at 0 and 0 here initially. And then we're at 0.6 atmospheres and we're at 0.8 atmospheres. And they want us to calculate the partial pressure of oxygen left after the reaction. There's your money question. When I solved this the first time, how many years ago, I went through a big old process of figuring out how many moles of all of these things were here. And I solved this as a conservation of mass problem, like we did the second week of school with a very similar problem. And it works, but I don't know that that's the best way to solve this question. I think it's better for me to use that note that I wrote on a previous slide that says partial pressures follow moles or mole fractions, because isn't a chemical reaction really just a ratio of moles, right? So what I think I need to know then is maybe something about I was trying to see if I could use something that allows me to figure out what the balanced chemical equation is with this one here. So I was trying to find a different way to solve this and rather than what I did the first time through this. But where would that give away my balanced reaction? I guess maybe what I could say about this is, do we see that in, this is in a different color. So this is the kind of stuff that goes in my workbook on the AP test, but wouldn't go on my answer document. That I recognize that 1 mole of this, if mole fraction and partial pressures follow each other, could we say that 1 mole of this produced 3 moles of this and 4 moles of this? Wouldn't that kind of work as a step towards a balanced chemical equation? Now I might, in my answer document, be willing to write in there that if this is a 1, this is a 3, and this is a 4. And now using the balanced chemical equation, or now using the partially balanced chemical equation, couldn't I just add up the number of oxygens on the product side and then put that in for the number of oxygens on the reactant side? There's no oxygens in the hydrocarbon, so all the oxygens that were produced here in the carbon dioxide and water had to come from our excess hydrogen. So I've got a total of 6 plus 4 more means I have a total of 10 in groups of 2. That tells me that this magic number right there is a 5. Okay, now what am I going to do with that? The partial pressures follow the mole ratio. So if this is reacting in a 1:5 ratio, then these have to be consumed in a 1:5 ratio. So 0.2 atmospheres reacts with 1.0 atmospheres. Wouldn't that be 5 times more, right? 2 to 10 ratio is a 1:5 ratio. So if 1.0 atmospheres of oxygen is consumed, how much is left over? 0.2 atmospheres. That's the way that whoever wrote this question wanted it to be solved. When I solved this my first time, I didn't see that. So what I had to do is I had to take each one of these numbers here and make it and find out what the N was. So N equals, PV over RT, solve and find that. When I did that, I got that the water came out to be 0.024 moles. I found that this is for the H2O. I found that the CO2 came out to be 0.018 moles. And that we already knew from part A that the hydrocarbon was 0.006 moles of HC. And then I just looked at these and said, okay, what's the mole ratio here? Well, that was a lot faster if we do it with partial pressures instead. Good times, isn't it? You guys having fun? On the basis of your answer above, write the balanced chemical equation. See, that's what I find interesting, is that part D really was what I used to solve part C. So that tells me that then they even had a different plan for this one. I don't know what their plan was, but they had a different plan. Mine ended up finding the balanced chemical equation first and then finding out how much was left over second. They had a different plan. If we knew what year it was that this was written, we could look at the answer key and see yet another option on how to solve this problem. Hey, look at that. There's still 9 minutes. We can do the second FRQ. Yeah? See, it looks on your face like, oh, man. I just want to remind you.
Mr. Fraser.
Speak up again.
That's not balanced because you had only 1 hydrogen and 8 hydrogens on the other side.
Okay. So we want to balance. You know what? I take it back, I take it back, I take it back, I take it back. Part D, I found the balance of the numbers. I never found the hydrocarbon that makes that work. You're right. I should have done that right away because that would have been an easy one. Thank you. Angel, that should be an extra credit point. 3 carbons, 8 hydrogens. There's your hydrocarbon, right? Because one thing we never did is we never did write what the chemical formula of the unknown hydrocarbon is. All I did was figure out how to balance the oxygens by using the products because they had oxygen in them. I never went back to balance the carbons and hydrogens, which is the part that Part D wanted us to do. So I guess that's the extension. So maybe they do have it written up like this on their answer key, because then with this, we could find out what the formula is, because that is, I didn't even read that. Thank you. Good now? Happy? Thumbs up? Thank you. All right, a student is doing experiments with carbon dioxide. Originally, a sample of the gas is in a rigid container at 299 and 0.7 atmospheres. A student increases the temperature of the CO2 in the container to 425 Kelvin. Describe the effect of raising the temperature on the motion of the CO2 molecules. You know what's so funny about this question here is this is what I was trying to write for your final exam yesterday. What I was doing was I started by saying, okay, you have a flask and you put some water in it, and then you put a stopper. And because you did that, the pressure on the inside equals the pressure on the outside. So I gave the atmospheric pressure. And then I wanted to drop a piece of carbon dioxide into the water, because we all know that when the carbon dioxide hits the water, it's going to immediately sublime into a gas. And the problem with it was I didn't know how to drop the CO2 in there without changing the volume of the water, which would then change the volume of air that's in the flask and affect the pressure. And I'm like, I can't write this. I can't figure this out without somebody like Maria saying, well, the volume's changed, right? So I quit. Now I figured out what I'll do for your final exam. You guys ready for this? You should probably push record right now. What if instead I took a flask and put it into a cold box that was like at negative 100 degrees Celsius, and I put a piece of carbon dioxide inside of there and put a stopper. And then we took this out of the cold box and put it at room temperature. Now this piece of carbon dioxide is going to sublime on its own inside of there and create a pressure. But before we even start this, I do want to have air in there at atmospheric pressure, because what I want is for you to be able to tell me that the total pressure inside the flask, once you remove it from the cold box, equals the pressure of the air, which will be the same as it was initially, plus also now the pressure of the CO2. Okay, but now I just lied about that too, because if you take it out of the cold box, the air inside of there is going to change pressure with temperature. I don't want to make the question too complicated that you can't solve it and have too much going on, you know? So maybe I just have to copy an FRQ like number 2019, number 4, where somebody's already figured all of this out. Hint, hint. Should I say it again? Hint, hint for your final exam. I'm going to find an FRQ. In fact, I'll be honest with you. The drawer right here was just opened up for me to pull out all of my excess FRQs from past years in order to start making your final exam. So just be ready that something like this one's going to be there. All right, how many minutes do I have? 4 minutes. Describe the effect of raising the temperature on the motion of the CO2 molecules. Anybody going to get that wrong? If you raise the temperature, what's going to happen to the particles? Move faster. Good answer. Calculate the partial pressure of the CO2 in the container at, it doesn't even say partial, calculate the pressure of the CO2 in the container at 425 Kelvin. Come on, how did 2019 have only 6 people pass the AP test out of 21 or 22? Please, how did they get this wrong? How would any of you, exactly, see, even Norton Antivirus even had a comment. Wouldn't everybody in here want to say the pressure equals, that's supposed to be an equal sign, but I'm just too upset, nRT over V? They gave you a temperature, originally a sample of the gas in a container. Oh, we don't even need to do that. They gave us a temperature and a pressure, and then we raised the temperature. To me, that just sounds like P over T equals P over T. That's basic chemistry. I could give that to my honors chemistry students in end of January, and they'll get that right. How did my students miss that? 2019 was a smart group too. So I don't know. Question part C, in terms of kinetic molecular theory, briefly explain why the pressure of the CO2 in the container changes as it is heated to 425. So you're going to say that the pressure increases because the particles are moving faster. You might even want to get all crazy and say an increase in temperature means an increase in kinetic energy, which means an increase in something in this formula. Since the mass hasn't changed, it must be that the velocity has changed. That's why the particles are moving faster. Because they're moving faster, they collide with the walls of the container harder and more often, right? So if you have a container here and you put a pressure gauge, when you raise the temperature, they collide with that pressure gauge mechanism harder and more often. There's your kinetic theory. The student measures the actual pressure of the CO2 in the container at 425 and observes that it's less than the predicted pressure in the ideal gas law. Explain this observation. Ooh, 5s. Look at all of you out there looking at this like, I want a 5 on the AP test. We haven't learned this yet. Here's what carbon dioxide looks like. It's a perfect ideal gas because it's nonpolar. Nonpolar gases make better ideal gases. But what did we learn when we were learning polarity? We learned that sometimes you can have what are called London dispersion forces, meaning that sometimes by just the random movement of electrons inside of a bond, the nonpolar carbon dioxide molecule might actually gain a slight amount of polarity, a slight overall negative side to this, accompanied by a slight overall positive side to this, would then induce the next carbon dioxide to do the opposite thing, actually look the same. Now, if that happens, two particles get married, they become one. If your particles reduce down because sometimes they stick to each other, you don't get as much pressure. So real gases don't ever give you as much pressure, actual pressure, as ideal gases. Because if particles can stick to each other, you now have fewer particles in there. Remember, the size of the particle doesn't matter. What matters is the number of them. So if two of them stick to each other, you now have half as many particles as you did before. Thank you for your attention. 9:19. You guys owe me 1 minute because I got you done 1 minute quicker than I said I was going to. Just kidding. You don't owe me any time. Thank you for your attention. You guys have a nice rest of your day. If you have any questions on your lab, send them. I'm sorry I didn't answer any yet because I haven't had a chance to look at emails. And if you have any questions on studying for your test, same thing. Don't forget, I'm going to be sending you a Zoom Chapter 5 test. You are going to enter the Zoom, and then the test is going to get posted to you, and you're going to stay in the Zoom while you take the test. At any time, if we discover that there's a problem with the test, then I am going to either announce it out loud if it's everybody's problem, or I'm going to write it in the chat. I'll probably do both. I'll write in the chat, there's a problem with question number 2. I forgot this word or I forgot this amount. Then when the first tests get turned in, I'm going to start telling people, okay, now you should be moving on to the last question. You have maybe 15 or 20 minutes left. After that time is up that I say your test is turned in, I start taking points away from the Zoom curve. Okay, so don't forget to Zoom with me on Thursday as you take your test. Thank you for your attention. I'm going to turn the recording off. Kumar had left me a note.